Okay, students, this is a review of the light-dependent reactions inside of the chloroplast. Remember, the light-dependent reactions are taking place in the thylakoid of the chloroplast. This diagram is helpful because it includes both photosystem 2 and photosystem 1. The other helpful thing about this diagram is the higher we are on the diagram, the more energy that part of the diagram contains. This is noted by the arrow on the left side. So let's get started. The first thing we know that needs to begin photosynthesis is energy from the sun. There it is, light energy. Little green dots at the bottom, those are our pigments, and they're going to absorb the sun's energy. When they absorb that energy, they are going to use that energy to take water. There it is at the bottom of the screen, H2O, and they're going to take that water and split it into its parts, splitting it into 2 hydrogens, 1 oxygen, which is noted by half of an O2 molecule. That's 1 oxygen atom, and 2 electrons. That's the most important thing, are those 2 electrons, because they're going to go up to the pigments and they're going to receive a lot more of that light energy, and they're going to get energized, which means they're going to move up on the diagram. These energized electrons are then going to be placed in our first electron carrier. This electron carrier, there it is. This electron carrier is part of photosystem 2. Remember, photosystem 2 comes first, photosystem 1 comes second. So this first electron carrier is part of photosystem 2 and part of the electron transport chain. There it is, noted by the proton gradient. That just means that as it's moving down, it is losing energy. As you can see, the arrow pointing down to a lower level on the diagram. So there they are, sitting at the top of the first electron transport chain, and more electrons coming from more water being split by the pigments are going to get loaded in that first electron transport chain, first electron carrier, and it's going to bump those set of electrons to the next electron carrier. There they go, right there. Every time they're bumped, notice they move down on the diagram a little bit. That means they are losing energy. And losing is not the best word. Really, it'd be better to say they are using their energy. They're giving some of it away, and they're giving some of that energy away to create ATP. Remember, that stands for adenosine triphosphate. They're taking an adenosine diphosphate, adenosine with 2 phosphates, and they're using the energy to add 1 phosphate to it, creating adenosine triphosphate. As long as you can remember ATP, that's fine. So this process continues. Now these electrons are bumped to another electron carrier, and every time they get bumped, more of that energy is used to create more ATP, noted by the blue arrow. And this process continues all the way down the electron transport chain until it gets to the 5th electron carrier at the bottom electron transport chain. Now, in this 5th electron carrier, notice it is much lower in the diagram because it's been giving off energy to make ATP. Well, these 2 electrons need to be re-energized if they're going to be useful, and they're going to get re-energized in now photosystem 1, our second photosystem. So they're going to get transferred to more pigments that are going to absorb more sunlight and there's our pigments, and re-energize the electrons, which moves them back up in the diagram because now they have more energy again, and they're going to go to the second set of electron carriers. There we go. They're loaded onto the first electron carrier in the second electron transport chain, which is part of photosystem 1. Now, this continues to happen as more electrons get energized again in photosystem 1 and bumps those out of the first electron carrier and into the second one. And once again, out of the second one and into the third one. As we can see, even in the third electron carrier, they still have a lot of energy because photosystem 1 has energized them. So they have a lot of energy. They're still very useful for doing things within the chloroplast, and so they're now going to be used in the Calvin cycle. That's our second set of reactions that take place outside of the thylakoid in the stroma around the thylakoid. So in order for them to get to the Calvin cycle, they need to be transported there, and they're going to be transported with NADP. Notice NADP has a single positive charge. When we load those 2 negative electrons, it takes on a negative charge. That negative charge is going to be balanced out by a positive hydrogen. thus forming NADPH. When we see NADPH, we know that there are two negatively charged electrons that are energized, ready to do some important work in the Calvin cycle. And that's where they're going to go. That is going to transport them or drive them over there. We can think of it as a UPS truck driving them to the Calvin cycle. And here's a note to help you remember that the Calvin cycle is another name for the light independent reactions which are located in the stroma. Now the Calvin cycle needs another energy source other than those two energized electrons being carried by NADPH. It also needs all of that ATP that was created in photosystem 2. So here's our arrow going the ATP from photosystem 2 to the Calvin cycle with the same note to the light independent reactions in the stroma. Hopefully this was helpful. Come see me if you have any more questions.